We're going to finish lesson 4.1 with graphing reciprocal functions. Whenever we graph, we need to identify some key features. The first thing you're going to want to do is determine your domain and your range for the function. What that helps you do is create asymptotes. And asymptotes are the same here as they were in topic 9. They're going to be boundary lines that our graph approaches but doesn't cross over. We'll also plot additional points using tables related to the domain. And I'll show you what that looks like with our examples. Now remember, a is the coefficient or the number that's on top of the numerator, kind of like what k would equal when we did inverse variation problems. If a is greater than 0, which means it's positive, the basic sketch of your graph should be in quadrants 1 and 3, always in opposite quadrants. If a is less than 0, meaning it would be negative, then it'll be sketched in 2 and 4. Let's take a look at our examples on the right. For 5a, we're asked to graph f of x equals 1 over x. This is known as the parent function. We haven't moved things around, we're not transforming it anywhere. So this will be the basic template for all of our graphs. In step 1, we're going to identify the domain and the range. Luckily, we have this problem up above. If you have a fraction, remember the denominator can't equal 0. And since x is in the denominator, we would say for the domain that x can't equal 0. And remember for our range, the output, f of x, that fraction also never has an output of 0. Super easy so far. So neither one of them can equal 0. Now, what that does for our graph is it helps us create our asymptotes. Now, the asymptotes are the actual equations for the boundary lines that we're going to draw on our graph. Since we have x can't equal 0 in our domain, we're going to say for our vertical asymptote that x equals 0, and that's going to be a vertical line. Since the output, the range, also can't equal 0, that's going to be the horizontal asymptote. And I'll show you that in just a minute. And we'll say y equals 0. So we're going to graph both of these vertical and horizontal lines with dashed segments. For the vertical asymptote at x equals 0, I'm just going to draw a dashed vertical segment all the way through, and I'm going to label that down here at the bottom, x equals 0. And I'll do the same thing at y equals 0. It technically just goes right along the x-axis. What we've done is we've now kind of separated all 4 quadrants. Now step 3 is going to include something from the domain. It says plot additional points using tables. So in step 3, we're going to use what we know about the domain to help us. We have a vertical boundary at 0. So what that means is we want to pick numbers that are on the left side of that boundary and then numbers that are on the right side of that boundary. That means we're going to generate 2 separate tables. In the first table, I'm going to pick values for x that are on that left-hand side. So I'm going to say x is less than 0. And then on the other side, we'll do the same thing, but we'll pick values for x that are greater than 0. Remember, we can't pick 0 because that's undefined. That's the restriction in our domain. So a number that's less than -0, I'm going to pick -1. And if we look back at our equation, 1 divided by -1 is in fact -1. Let's go ahead and plot that point right down here in the corner. If I pick -2, watch what happens. The equation is 1 over x, so 1 divided by -2 is -1/2. A little bit more challenging to draw. If I go to -2, I'm going to go down just a little bit more. If we went all the way over to -8, for example, that would be y, or 1 over -8 for our output. So -1/8. Super close to that red boundary line, but we're not crossing over. Here's the trade-off. If we actually go to -1/2, so between 0 and -1, 1 divided by -1/2 would actually be -2. So at -1/2, we're down here at -2. What makes this graph unique is it's super, super close to both the vertical and horizontal asymptotes. If we draw a curve through those given points and we go left and right forever, the graph will look something like this. Notice it's pretty challenging to get those points in there, so try the best you can to make that curve happen. Now over on the right, we need to pick values for x that are greater than 0. I'll do +1, +2, +8, and +1/2, just picking values on the x-axis that fit our domain restriction. 1 divided by x, well 1 divided by 1 would be 1, so it puts it up here in quadrant 1. If x equals 2, 1 divided by 2 is +1/2. So again, we're going to kind of just go towards that horizontal asymptote. 1 divided by 8, even tinier, way over there, super close to the bottom of that boundary line. And then if we do 1 divided by 1/2, you actually get +2. So at 1/2, we're up here. Again, try your best to connect the dots that are given and going towards each of the asymptotes on the left and right-hand side. And there you have the parent function for a reciprocal graph. Now, obviously, we're not going to just leave them here. We're going to move them all around. Let's take a look at example 5b. In example 5b, we have g of x is equal to 1 over x minus 3 plus 2. Thinking about our transformation rules from semester 1, notice in our denominator we have x minus 3. We would describe that in words by saying that it moves 3 units to the right. So we would say moves right 3. And then does anybody remember what this second part would do to the graph if we describe that? If +2 is being added after what's happening to x, it's going to move it up 2 units. So if you thought up 2 units, then you're good to go. Now, what those descriptions are going to do is actually affect our domain and our range. For our domain, remember the denominator can't equal 0, so that means x minus 3 can't equal 0. If we move 3 over, we would say that x can't equal 3. So from the parent function, if it moves right 3, that would make sense. For our output, if x can't equal 3, that means that fraction can't equal 0. And if it can't equal 0, but we tried to add 2 to it, that means our output can't ever equal 2. So I almost wrote f of x. G of x can't equal 2. That's second part for our transformation. So that's step 1. We kind of described what was happening in words, and that helps us determine our domain and our range. From here, we're going to create our asymptotes, or our equations for our lines. If x can't equal 3 for the domain, that's our vertical asymptote. We just write x equals 3. The range creates our horizontal asymptote, and that means y is equal to 2. So you'll notice on our graph, we're going to move those over 3 right and up 2. If you draw your lines in, you'll notice that we kind of shift the x and y axis over into quadrant 1 a little bit. So we still have kind of quadrant 1 over here on the right, quadrant 2 on the left, 3 on the bottom, and then 4 on the bottom as well, but on the bottom right. We're kind of moving it over in that direction. Now let's see what ordered pairs we can create and determine how that's going to affect the shape of our graph. To create our tables, remember we always go back to that vertical kind of boundary right here at x equals 3. What that means is we want to determine values that are less than 3 and then values that are greater than 3. By doing that, we'll generate points for our graph. If we pick points for x that are less than 3, we'll be able to get that curve on the left-hand side. But look at this, everybody. We have to plug that in for x and then simplify that entire problem. It's not that bad. It just looks a little tricky. If we pick a number that's less than 3, let's try 2. If I plug in 2 for x, 2 minus 3 is -1. 1 divided by -1 is still -1. And if we add 2, that puts us at +1. So 2, 1, just like that. Not so bad. Let's go over to 0 and see what happens. if we go over to 0, 0 minus 3 is negative 3. 1 divided by negative 3 is negative 1/3. Negative 1/3 plus 2 would be 1 2/3. So still a little tricky to graph, but we'll get there. If we keep going, the numbers are just going to get smaller and smaller. Let's go a little bit closer to the boundary line. Instead of 2, let's go over to 2.5. If we do 1 divided by 2.5, we're going to get exactly 2. And if we, wait a minute, not exactly 2, wow. If we do, oh, sorry guys, if we plug in 2.5 for x, my head was not in the right space there. 2.5 minus 3 is negative 1/2. So 2.5 minus 3 is negative 1/2. 1 divided by negative 1/2 is negative 2. And then negative 2 plus 2 will give us 0. Let's plot these 3 points on our graph and see if we can get an idea of what that curve should look like. If you plot those 3 points, you can see the trend of the curve approaching both the vertical and horizontal asymptotes. As long as you can kind of tell where that turning point is at 2, 1, and you have other points plotted, draw a smooth curve through the 3 of those that go to the edge of your graph. As you can see, it gets really close to those boundary lines. All right, let's take care of the other side. Looking back at our graph, if we need values for x that are on the other side of that vertical asymptote, they have to be greater than 3. Let's try 4. If we plug in 4 for x, 4 minus 3 is positive 1. 1 divided by 1 is 1, and 1 plus 2 is 3. Now, if we think about that as our turning point, let's go back down to our graph. We know that our graph should be in quadrant 1 because they're in opposite quadrants. If we plot 4, 3, that matches up with our transformation. From here, now all we need to do is draw that curve that's going to go edge to edge, mirroring the graph, the portion of the graph on the left side. I know it can be pretty challenging to draw this in, but notice we've done the transformation of our parent reciprocal function. And that finishes up our notes for lesson 4.1.